Chairman. I'm Rosalia Fitz from Polytechnic University of Bari. I'm PhD and postdoc researcher in Polytechnic of Bari, and I'm going to discuss the presentation which is focused on the fatigue behavior assessment of IFP material that was produced by automated fiber placement. They are CFRP. In particular, we performed the thermal signal analysis in order to assess, to correlate the stiffness reduction of the materials by using the thermal signal to the stiffness reduction of the materials. And the importance of producing high-strength materials by innovative technological process is useful, capable for reducing the time to market of components, but the complex damage mechanism of these materials requires the suitable experimental technique for their characterization. But first, let me to briefly introduce the basic contents of this presentation. I will speak about the state of the art, referring to the models for represent the degradation, the reduction of mechanical properties, as well as the capability of the infrared thermography to study this phenomenon. I will present the aims of the research, the experimental campaign. I will switch into the data processing results, and finally conclusion will be drawn. Okay. The idea is I fatigue testing and I have some energy, and by using thermography, by using temperature, I can represent the component, the portion of the energy, because since the energy is, the temperature is a sentinel, a parameter for evaluating its sources involved in the fatigue. In particular, the first harmonic component of temperature is relating to the mechanical properties variation, and in this work will be used these for study the reduction of mechanical properties. But what is interesting is also this ED, this energy, which is relating to the energy of hysteresis loop. As previously said, it is a useful parameter used in during fatigue fracture mechanic assessment of the energy, as we presented before, because it is relating to the second order temperature variation, which increase due to the elastic strain, during the hysteresis loop. But whether or not the material, the composite, is produced by IFP process, what is interesting to see is such that the reduction of mechanical properties can be described by using this function as microcracks, as transversal and longitudinal ply crackings occurs, and finally fiber breakings also occurs together with the damage accumulation. And this also determines the fact that the crack propagates in several directions different from the fiber angle. So this led to a difficulty in defining the constitutive equation, and then the suitable modeling thanks to the suitable experimental technique is necessary to validate this model. In fact, we found that longitudinal cracking and also transverse ply crackings are the most important causes of failure or stiffness degradation in the composite material. And as just presented in literature, the Young modulus, the longitudinal Young modulus, can be related to the stress by using a power log passing through the crack density. And it is very interesting because the thermographic, a thermal parameter, behaves roughly in the same way as will be shown next in the text. But the capability of infrared technique has already been discussed. In fact, it is also used for assess the endurance limit, the fatigue resistance at specific number of cycles, the runout, or the use of thermoelastic source for evaluating the mechanical properties variation is also very well known in literature. So, which kind of advantages we can catch by using thermography? Essentially, the rapidity to make the test and to make also the analysis, but also the fact that by performing a suitable algorithm to extract the components of temperature, we can assess localized information referring to the damage occurring in the material. And this is why the aim of the present work is to correlate thermography, specifically the first harmonic amplitude of temperature signal, to study the stiffness degradation of the material. But to do this, we use the composites obtained by AFP process. The automatic fiber placement process is rapid, is accurate process to depose from 1 to 8 toes of material. Toes of materials are deposed as ribbon. A series of ribbons represent the panel. And robotic arm with 7 degrees of freedom can depose simultaneously this toe, and it is equipped by a robotic head, which sometimes is also equipped by exciting external sources such as a laser, and in order to obtain the pressure, the compactive pressure to process the panel. The panel we used was presented the stacking sequence, a quasi-isotropic stacking sequence, and by using and according the standard STM 3039, we designed the samples from this panel. We used a loading frame of 200.5 kilonewton to test these samples, and an infrared thermal camera of FLIR series 6XXX with a noise equivalent temperature difference less than 25 millikelvin to acquire both the tensile test and constant amplitude test. The tensile test was performed over five samples, while the constant amplitude test ranged in the amplitude in the maximum stress between the 50% to 8% of ultimate tensile of material. And we assessed the endurance limit, that is the resistance, the strength of the material at a specific number of cycles, 2 millions, which was in correspondence of the 50% of ultimate tensile test strength of the material. The first data processing involved was carried out on tensile test in order to understand which was the damage which occurred in the material. In fact, we can see that the thermal signal, the monitor thermal signal, was roughly decreasing for all the tests, and we can see that the loss of linearity of the material was in correspondence of the appearance of damage in terms of crack in the matrix, and as also confirmed by this max, which represents the maximum of the signal and the time at which the maximum appeared. So, by analyzing the data, we find that the onset of the damage and the loss of linearity was in correspondence of a stress which was less of the endurance limit of the material. But apart from this, the signal reconstruction algorithm allowed us to obtain the matrix we used to measure, to compare the stiffness and assess the stiffness degradation of material, which was the first harmonic amplitude of the temperature variations. Clearly, the rough data, pixel by pixel was extracted this component, and we studied this component to perform the analysis. So the first step was to assess the thermal matrix, the correct thermal matrix. Roughly 10 years ago, Professor Barton studied that by studying the thermoelastic stress analysis, she found that when a composite undergoes cyclic load, the signal referred to undamaged condition present a maximum and a minimum. Both maximum and minimum increase in positive and in negative sense. So we use the second percentile value as a matrix to study the stiffness degradation of the material. In fact, this adopted matrix, that is, as previously said, the signal referred to undamaged condition, behaves like this for all the tests performed of the constant amplitude test, and we can see that there is a steady state, but it's not, it's just stop the graph, it continue, and the steady state and a severe slope at fixed number of cycles, and referring to the mechanical data, which was acquired by using an extensometer during the test, it is possible to see roughly the same behavior, which is composed, as is possible to see also in literature, by a decrease and a stabilization of the signal as the stress increase. And by comparing the two metrics adopted at fixed number of cycles, it is possible to see that there is a higher sensitivity of the thermal parameter, the thermal matrix, to represent the degradation, the reduction of the stiffness. In fact, we can see that a severe sloped variation is possible, is present before 10% of total life of the sample. We respect the less severe slope variation of mechanical data. But by representing together this behavior in terms of absolute value of the thermal parameter, it is possible to see they can be represented by a power law. In fact, by manipulating the model which was present in literature, it's possible to see that thermal matrix and stiffness degradation are related by a power law, which coefficient can be assessed by performing experimentally. In fact, we use the sample at higher stress to model the data, and we apply this model to all the other stress level. In fact, we can see that all the points referring to all the tests belong to the 95 confidence level, confidence bound fixed for this test, even if there is a borderline value at higher stress, maximum stress at 75. Maybe it can be due to the fact that the signal does not stabilize at this stress value. But however, all belong to the confidence bound. And finally, the final validation has been we proposed is carried out on the stiffness degradation model related to the duration between the number of cycles and the total number of cycles, and this model was applied to the 50% of ultimate tensile test sample, and to the sample test that 65% of ultimate tensile strength of material, and it is possible to see that all the data belong to the 95 confidence bound level of the material, so that the model data can be fit roughly well with the data, the experimental data. And finally, so in this presentation, a preliminary study, preliminary correlation between thermal data to the mechanical data is presented, and possibly a model is proposed in order to predict which is the degradation of the material, of the mechanical properties of the material cyclically test at constant amplitude test. Thermography is rapid, is accurate, and also allow to a local analysis of the damage in the structure. Then is very useful and capable experimental technique to validate numerical model. Future developments will be devoted to the study, the relation to relate the second harmonic amplitude temperature variation to the energy of hysteresis loop in order to provide another model to predict damage in the material. Thank you. Sorry for the late.
So it's okay.